So welcome along to the next video in this series called In Search of the Northern Lights. My name is Dr. Alan Wood and I'll just do a screen share here and we'll pick up the PowerPoint for today's presentation. So if I just hit from current slide, we'll get underway with this PowerPoint. So we've been talking about the Northern Lights, these absolutely beautiful patterns of red and green and purple in the night sky. I know I've shown you these pictures before, but they're so beautiful, I thought I would show them again. We've talked about how the ultimate source of the Northern Lights is the sun. We've talked about the transitions in the atmosphere that cause these particular colours. We've talked about how we can establish the height of the Northern Lights and why the green Northern Lights are typically at a lower height than the red Northern Lights. And at the end of the last session, I posed a couple of questions. I said, well, if we look at the Northern Lights from space, we can find something called the auroral oval. The auroral oval are the locations at which the Northern Lights are most commonly seen. And when we see the auroral oval, it looks a bit like this. So you can see it's centered on something, but it is not centered upon the geographic North Pole. We can see the top of Scotland here, we can see Norway here, and the geographic North Pole is somewhere over here. So what is it centered upon? And then why are the Northern Lights commonly seen in different countries in different eras? How does that follow from this? So first up, what is at the top of Greenland? And what's at the top of Greenland is the geomagnetic pole. You know how if you've got a compass, it doesn't quite point to true north. If you followed the compass needle north and north and north and north and north, you wouldn't get to the geographic North Pole. You get to the geomagnetic North Pole. It's at a slightly different location. So why are the Northern Lights commonly seen in different countries in different eras? A couple of hundred years ago, they were much more common in Scotland than they are now. Well, that's because the geomagnetic pole moves. This little plot here shows how the geomagnetic pole moves over time relative to the geographic pole. So the geographic pole is right here in the center of this plot. And what you can see is in some eras, it doesn't move very much. So if we look, I don't know, between 1700 and 1800 here, it hasn't moved very far. If we look between 900 and 1000 AD, you can see it's moved quite a way. And so the geomagnetic pole moves over time. So if we look at the auroral oval over time, we would expect it to be in different places. So if we look back to, say, 1700s, we find the auroral oval here sitting over the top of Scotland, going through southern Norway. So if we look at somewhere like the island group of Svalbard, where we've talked about where I've shown you some beautiful movies from the from the Northern Lights in the past few sessions, but it's nowhere near the auroral oval in 1700. Let's go back to 1500. If we go back to 1500, what do we see? Well, if we go back to 1500, then we start to see that the auroral oval is now nowhere near northern Scotland. It is now over northern Scandinavia, over here. If you go back to 1200, the pattern's different again. 850 AD, the pattern is different again. We see this changing over time. And that's one reason why the Northern Lights are commonly associated with different places in different historical eras. Because the auroral oval moves over time, and in fact we can see some evidence for this. Matt Owens and colleagues at the University of Reading have done some absolutely brilliant work on this. They've been looking back in historical records about occurrences of the Northern Lights. Where did they find these historical records around about 1700s? Well, they find them from things like newspapers. They find them from things like people's diary records that people might have kept and historians use now. They find them from things like church newsletters. In the round about 1700s, we would expect the Northern Lights to be visible about 2 or 3 times a week from northern Scotland if the skies were clear. And based on some of the historical records, this all seems to tie up. So the auroral oval moves over time. But even so, when we talked about our historical observations in the first of these videos, we were saying that our earliest observations seem to be cave paintings from France from 30,000 BC. They're possibly mentioned in Chinese writings in 2600 BC. They were observed in Greece in 450 AD. None of those are places where we would really think of the auroral oval as being. They're too far away from the pole. So also what we need to consider is we always get some extreme events. And extreme events will drive space weather processes and will drive the northern lights further down towards the equator. And what we find is that if you think about say the southern bit of the UK, they are fairly rare. But maybe once every few years, the northern lights might be visible there. If you go down to the Mediterranean, if you go down to the Mediterranean, again, very, very rare, but still sometimes observable there. If you go down towards the equator, once every 100 years or more, they might be visible down there. And so what we find is there's always some large extreme events. Now, as well as creating these beautiful displays of the northern lights at all sorts of other locations, these can have implications for technological systems. And we're going to come back to that in some of the sessions next week. What I want to talk about first, though, is this whole thing about the geographic pole and the geomagnetic pole. Now, it was noticed in the 1400s that compasses did not point to true north. They're pointing to somewhere else, they're pointing to the geomagnetic pole. And in 1635, it was established that the position of the geomagnetic pole changed over time. Now, the auroral oval is centered on the geomagnetic pole. It's a magnetic effect. Now, in 1724, researchers in London saw that variations in the magnetic field were associated with the northern lights. So changes in the Earth's magnetic field seemed to be related to the northern lights. And then this led to a prediction in Sweden. Variations in the magnetic field were observed. And the northern lights were predicted, and about an hour later they turned up. And that we believe to be the first successful prediction of the northern lights, or indeed any space weather phenomena. Why? Okay, we're quite happy with the idea they might be centered on the geomagnetic pole. But why do we have disturbances in the Earth's magnetic field associated with the northern lights? Well, let's start off by thinking about how a charged particle behaves in a magnetic field. The magnitude of the force that's experienced by a charged particle in a magnetic field is given by this equation here. F, the force in newtons, equals Q, the charge of the particle in coulombs, multiplied by V, the velocity of the particle in meters per second. Then we've got the cross product with the magnetic field, where the magnetic field is measured in Tesla. Now, what does this cross product mean? Well, cross product means if we just want to know the magnitude of the force, we don't need to worry so much about the cross product. But where it's really useful is thinking about the direction of the force. And that we really do care about. The cross product tells us that the force acts at right angles to both the direction of motion of a charged particle and to the magnetic field. So if we've got the velocity of a particle in one direction, we've got the magnetic field at right angles to that, the force is at right angles to both. So let's just suppose, for example, we've got a magnetic field line coming out of the screen as shown here. Then we might have a charged particle, an ion, moving around that. So as it begins to move, imagine it's just here and it's moving downwards on the screen. Well, it will experience a force. Its velocity is downwards, the magnetic field is out of the screen, and therefore the force it experiences is at right angles to both of those. And that force at right angles deflects this ion to go around and round and round in a circle like this. So what we see is these charged particles, these ions spiraling around the magnetic field line. We can calculate the radius of this circular path, and that's called the gyro radius. So we can find the gyro radius. It's also called the Larmor radius. The two terms are interchangeable, and it's given by this expression here: RC equals m, the mass in kilograms, multiplied by the velocity in meters per second, divided by the charge in coulombs, and divided by the magnetic field in Tesla. So what happens if we've got, say, a positively charged test particle, an ion, going into a region where we've got this magnetic field coming out of the screen? Suppose it's over here, it's ambling along with some particular velocity. Well, it goes into this region, and of course, its motion is deflected. It begins to curve. It starts to spiral around the magnetic field lines. Of course, it's still got that component of velocity from before it entered this region, and so it follows this curved path like this. If we had an electron, a negatively charged test particle, well, then it starts to move in the other direction, and we get a path rather like this. Why does it move in the other direction? Well, because the charge has the opposite. The charge is now negative rather than positive, and that feeds through into the equations. So the deflection depends upon the charge, the velocity, and the magnetic field strength. So we're going to finish here with a question. In fact, two questions. Suppose we've got this situation here. You can see we've got a magnetic field of varying strength. Here I've drawn loads of magnetic field lines, so it's strong. Here I've only drawn a few, so it's weak. Draw how ions move in this magnetic field. So suppose we've got this ion spiraling around the magnetic field line like this, very happily. Well, it's not going to keep doing that because it goes into regions of stronger and weaker magnetic field strength. So what is going to happen as a result of that? You might find this formula here very useful when you're sketching out what happens. Think about which of these terms vary and how does it influence RC, the radius of curvature. Then what would happen to electrons? So I'll leave you to have a think about those, and we'll go through the answers to those on Tuesday of next week. And when we go through those answers to those, we'll also look at why why we might then expect the northern lights to be associated with disturbances to the Earth's magnetic field. That will then lead us in to think about the applications of not just the northern lights, but space weather. And then the final big strand we'll talk about is about how we can go looking for the northern lights ourselves. So thank you very much for your attention. Have a great weekend, and I hope to speak to you on Tuesday.